Yes, thank you very much to Peter and the other organisers for hosting me. It's my privilege to be your first guest speaker. Um, I'm going to talk to you about Atom Probe Lab, and the background of this is it's Matlab code that I started when I was doing my PhD in Oxford way back in 2011. So I think, as I mentioned previously, Matlab has changed a little bit since then. It's been, I don't know, maybe a slightly bumpy road. The main reason for choosing Matlab then was there was actually a scientific computing course. It was taught sort of equally in Matlab and Python, and the Matlab side of things was basically just easier. I do use Python. I use other programming languages as well, like R and C++. But this is the Matlab side of things. I'm very much hoping that this can be integrated in to the work that Peter is working on with the Atom Probe toolbox. So that's the kind of context. I'm going to be talking. I've centered it mostly around composition, uncertainty, and peak overlaps, mostly because I'm reusing a previous presentation. So forgive me for that. But we're going to dip into the rest of Atom Probe Lab and see some of the other useful features, hopefully, as well. You should have downloaded the latest zip file, which includes a live script and a PDF output of the live script. So even if you can't get the live script to work for whatever reason, you should be able to read the PDF and get an idea of what's going on. And so when we get to the Matlab practical bits, then you have to follow along with that. I guess I'll go through that as we get into it. So I can't click. There we go. Solving peak overlaps introduces uncertainty. That's what we're going to find out. I'm going to demonstrate a method for quantifying the uncertainty and show that we can use this to improve our composition confidence intervals for experimental planning and data analysis and everything in between. So I'm going to cover a little bit about uncertainty in general, specifically about counting error, overlap solving, maximum likelihood estimation, fitting and bias. And like I said, I'm also planning on covering some stuff on mass spectrum plotting. So I have my own plotter, which I think looks quite nice, simulating mass spectra, and making peak overlap diagrams. If there's time, we can look at solving some peak overlaps, say from a line profile or maybe from clusters. And I'll give you a demo of that. That's the kind of like main bulk of the I guess I'll call it a toolbox, even though it's not packaged as one. So just very briefly, the difference between accuracy and precision. So if I put my laser pointer on, if we're accurate and precise, we are close to the true value, which we don't necessarily know, and there's a small spread in the results. If we are inaccurate, then we're far away from the true value. So here that's represented as not being on the center of the bullseye. But the precision relates to the spread. So if we can repeat the same experiment, we get different answers. Now, we're probably somewhere down here in our atom probe analysis that we're inaccurate and imprecise. And that's not necessarily, being inaccurate is bad. We'd like to think that we were accurate. But being imprecise isn't necessarily bad as long as we know how imprecise we are. Calibrating accuracy is really difficult. And that's normally where standards come into play. But with atom probe, it seems quite difficult to establish good standards because every individual sample that you run has different voltages and evaporation physics and background, and the shape of the tip is different. So how the laser interacts with it is different. So there's a lot of parameters that are actually really hard to control in an actual atom probe experiment. I'm kind of going to assume that we're mostly accurate for what we do when it comes to boiling it down to the peak counts. And that may be a flawed assumption, and we'll get to that. So just to give you an example, if we've got two findings, finding 1 and finding 2, which one of these is significant? If these are the same error bars, then finding 1 is much more significant than finding 2. So our quantification of uncertainty alters our interpretation, and it can alter it quite drastically. There's a great paper here I recommend you read, especially how people misunderstand what error bars mean. For example, fun fact, if these error bars are one standard deviation and these ones are 95% confidence intervals, I think they're more or less equivalent. And I found that surprising. So there we go. It's not always straightforward, and I think we have to be aware our target audience doesn't always know exactly what we mean. So there's tons of sources of uncertainty in Atom Probe. In our position, we have trajectory errors, surface reconstructions, surface migrations. We have all of the influence of the detection in electronics, and that affects the time of flight as well. In the time of flight, we have uncertainty of the departure of the ion. We have the timing error, which is reasonably well known. We have uncertainty in the path length. I mean, we always, quote whatever the path length is in millimeters, 382 millimeters for the 3000, I think, XR. But there's actually a bowl correction that we do. So every tip has its own small change in flight path. We also have some evaporation effects or bonding, some sort of physics, and these give us sort of broadly spatial uncertainty and spectral uncertainty. So I'm calling that peak shape. So mostly when we look at mass spectrum, when we're looking at a mass spectrum, we're looking at the peak shape, and we all know that the peak shape in Atom Probe is quite variable. Position and identity they are somewhat linked. So in this case here, these different clusters, the ones that are more blurry, the ones that have more positional uncertainty, are actually harder to define. And in that way, our composition kind of depends on the localization of our data set. So this is actually the same data. I just literally like Gaussian blurred the clusters out here. So if this happens, you might end up measuring a different composition. And I'm not really going to... So I'm not talking about this at all. I'm just highlighting is it something that I think we can often forget, especially if we're just looking at the ions and we forget about the spectral side of things, or we just look at the mass spectrum and we forget about the position, that it's all kind of interlinked together. So this is a paper that Stella was working on, looking at some kind of tricky superconducting materials. The oxygen content was really, really well known here because this material would not be superconducting unless it was within these two very narrow bounds. And what we can see is the Atom Probe analysis as a function of laser energy, so that the laser energy was increasing and or decreasing and then increasing and going back to the start in a loop. We can see that the oxygen and the barium, for example, they kind of change. The copper is systematically above what we would think. And what's hidden in this plot is actually the difference between the low and the high laser energy. The mass spectra look very different because the peak shape is different, because the peak shape depends on the thermal properties. The charge state ratios change, obviously, as you change the field. So you've got all of these different effects. Maybe your peak overlaps are changing, your peak shape is changing, and your background might be changing. And all of this is getting boiled down into your interpretation. So there's actually a lot buried in our interpretation when we get down to composition. So it's complicated if you want to get accurate composition. So what we aim to do is to measure the composition of a specimen before it's evaporated. So that's what we're aiming to get at. Our detector only measures timing data. So it doesn't even measure position, it measures timing data, and we have to turn that into position and time of flight. So, on the detector, these things are linked together. We have finite mass resolving power, so we end up with a specific peak shape, and that might be, a fundamental difference, or that might be just like blurring on the detector. Our starting point for quantification is to extract the counts from each mass peak. And that sounds really simple, but then you've got, well, what is a mass peak? So peak detection. We have to put, maybe we want to put a range, or maybe we want to fit a peak shape to it. We need to subtract a background. Maybe we've got, another approach. Maybe we're doing this kind of blind deconvolution approach here that Johnson showed, or peak fitting. I'm going to just assume that you can get the counts for each range or each peak accurately, and I'm coming around to the understanding that that's increasingly not necessarily the case. But let's just assume that for talking about composition because it simplifies things. So that gives us our from our mass spectrum back hopefully to our our counts back up here. So this is what's happened. The atoms evaporated, we get ions, these give you different isotope peaks, and then we've got the mass spectrum binning, the peak shape, and the detection, which gives us our actual mass spectrum that we're looking to kind of undo this and get back to the truth, which is what our material was. So then we start quantifying things, and I think of this as kind of like a stack that we're building up. So we've got the easily and easily and well understood components. You can start with counting error. Then we want to figure out what ions we've got. So you've got ion identification. So we have to make a choice about what ions are present. And if you don't choose an ion, it's not going to show up in your sample. If your sample has got copper in and you don't say it's got copper in, it doesn't have copper in. So we've got the ranging, so the range widths or peak fitting or whatever it is you're doing. We've got background subtraction, so the global background or local backgrounds. And then maybe we have multi-hit problems that are even more nuanced that come into this and are affecting our composition. We have our reconstruction as well, which affects where the ions are, and that might make a difference as to how we interpret our results. And at the end of the day, hopefully, we can develop a fancy new paper that actually depends on all of these things. And so if one of these blocks is actually faulty, then maybe our whole stack of analysis can fall down. So I've got my nice Jenga animation here, and hopefully that doesn't happen. But that's kind of what we're doing with necessary, maybe without realizing. So someone once said, "I don't think peak overlaps are that important," and that person was me, circa 2013. And this was in response to a presentation that I gave in the Oxford Materials Department. And yes, I was asked, have you considered the effect of peak overlaps in your data? And I was like, no, they're not that important. They were important, actually. So some years on, I can tell you, I'm not going to say that I have all the answers. And I'm not trying to say that everything that you've done previously is wrong. This is science. We aim to improve. We want to learn from one another. We should be objective about our data. We shouldn't get upset because we find something that someone else has done better or suggesting that we've been wrong. We shouldn't take that personally. We're trying to improve the systems and progress the field uniformly. There are some really good examples of how to deal with uncertainty in Atom Probe in various different aspects. So I'm not saying that that's not been done correctly. There are some really good examples. It's just usually it's only added as an afterthought, like, oh, we need some error bars here, so let's add some on. And often it's only the counting error which is reported. And that's not, counting error is going to be the smallest possible source of uncertainty. So you might be really misrepresenting your result if you only include counting error and don't include anything else. So just as a quick aside, I talk about peak overlaps. So if we've got these two ions, ion A and ion B, I would say, so this is like a stacked histogram. You wouldn't see this, you just see the outline of the total in your experiment, but actually there's two different peaks hiding in here. So I would call those overlapped. People also talk about interferences. Or mass interferences or interferences. I think in geology that's popular. So I'm going to say these are peaks that aren't resolvable with the mass resolution of the instrument. And then if you want to figure out how much of these different ions you have, I would call that process overlap solving. Okay, so it can be a little bit confusing, but here are our peak overlaps. And then we can also have a process. I'm representing it here as deconvolution. So people do call it deconvolution, and in a weird kind of technical way that you could consider that correct, because what I call the overlap solving process is actually kind of like a discrete convolution of the peak of the ion counts with the abundance into the different isotopes. So it's kind of like a deconvolution, but in signal processing, deconvolution is a very well defined thing. You have some point spread function, which is your peak shape. Deconvolution just turns that into a delta function, which is what I'm trying to represent here. So we've taken all of the counts from B and from A, and now they're just single blocks. So I don't really like calling it deconvolution, because in Atom Probe we might want to do deconvolution to sharpen the peaks or remove the effect of the peak shape. There's also decomposition, which I think can be confused with converting ionic and molecular species into elemental ones. So, H2O into hydrogen and oxygen. That's the decomposition process. So I like to talk about overlap solving. So sorry for laboring that, but I think nomenclature can be important. So let's just do a quick counting experiment. And I've got a demo in the live script, which we're going to get to demonstrate this actually working. So you can kind of play with it yourself. Imagine we've got a bucket full of different coloured dice, and these different colours represent our different species of ions. Our atom probe experiment is it's fundamentally a counting experiment. We turn the detector on, we count for some time, and then we turn it off, and we've got some number of counts in some mass bins at the end of the day. Therefore, we can use a whole bunch of statistics and probability to understand the uncertainty in the processes that are going on. We can use dice to kind of visualize this stochastic process. So there's a random chance. If your composition is 50-50, it doesn't mean you're always going to get A and then a B. Maybe there's an argument if you're looking at an ordered alloy that there is a non-kind of random element to what you're looking at. But in general, I'm going to assume if you've got a composition like a lump of stuff and it's homogeneous, that the ions you draw from it are random. So here we've got some dice, we've tipped them out, and here they've got different numbers on. So the numbers here represent the mass peaks, and the colours represent the different species. So if we've got two different dice, the distribution of the numbers on the faces represents their kind of natural abundance into these different sort of isotopes. So A, for example, has equal abundance in peaks 1, 2, and 3, and B has equal abundance in peaks 3 and 4. So it's quite simple. On average, you'd expect to get a 1 a third of the time with A, and with B, you'd get 3 half the time. So our ideal result, if we have 42%, roughly 42% A, would look maybe something like this. So we're going to tip out a bunch of die, and then we're going to look at the numbers and count them up. So if we actually do this, and I've got a little kind of graphical representation of it here, this is the actual composition of A that we get in each experiment. So where we know what the colours are. And you can see that it builds up this nice kind of, it looks kind of Gaussian. It's actually binomial because an individual result is either A or it's not. So the result here is a binomial. In our actual experiment, we can't tell the difference between black and blue. So information is going to be lost at this peak here in the middle. So with the actual true composition, we can model this very well using the standard atom probe result that hopefully we all know and love. And this is the actual counting error. So that's the equation that we use to get the standard deviation. This just comes again from binomial theory. Now, where we have peak overlaps, say at the 3 number, it could be A or B, and we don't know the amount. Information is lost at the detector because our detector is mass to charge sensitive, so number sensitive, and not color sensitive, so not element sensitive. So just going back to here, it can see the numbers, but we're colorblind to the actual identity of the ion, to the color of the dice. So in this, there'll be no separation between black and blue. You'd just see a peak. You wouldn't know how much there were. Maybe if you had a kinetic sensitive detector or something and they had different charge states, you could figure that out. We don't have that. What I'm going to present is a model data approach to estimating the true composition. This is where the maximum likelihood comes in. We have some measured data. We propose a mathematical model that explains that. And then hopefully we don't introduce any bias. So whatever we do, we're going to have to make a guess at the potential ions involved, and they're going to need to be part of the model. So in statistics, there's a mantra that all models are wrong. If you model something, your model is not going to be reality. If you guess which species are involved in your spectrum, you might be, there's a very, very small chance that you get that correct. And there are lots of possibilities where you get that wrong, where you miss one of them, or you include an extra one. And anything where we're missing or including extra things is going to introduce bias. So that's inaccuracy in our results. There's several methods for solving these peak overlaps, which I'll just briefly cover, and then I think I'll jump to MATLAB. So the first method is what I'm calling the single peak method. So you have one non-overlapped peak, and you use that to figure out how much must be in another peak. So this is very straightforward. You can do this in Excel without any difficulty at all. If you're just using one peak, it's a very inefficient use of the data. So if you're just using peak 1, you've got the data from peak 2 and peak 4, which you could also use. You've even got the data from peak 3. But if you just use a single peak, this gives you a biased and inefficient use of the data. Another thing you can do is you can minimize the least squares. So if that's the actual observation, those are the red crosses. If we assume we have a perfect distribution each time of the A elements and the B elements, so this is using that kind of natural abundance, so that our prior knowledge of what the dice faces are, then we can fit the residual, minimize the residuals of these crosses. This is generally what we do in science. Like, it's our go-to thing, use least squares. It assumes, and this is key, that the error, the normal, the residual here on each of these is normally distributed, which is not the case when you have count data. So when you have count data, we can think of these bars as being Poisson distributed, and that's not normal. So you can't have the error here. Can't go below, your actual observed count can't go below 0. So it can't be normally distributed, because a normal distribution, goes plus or minus infinity. So especially when you get to small counts, least squares is going to be worse. And there's another option called maximum likelihood. The fit is actually different. If I just show you here, it doesn't make much difference. But this is using a more complicated mathematical model to fit the most likely result. So you don't really need to know exactly what that means. If I'm happy for you to take away that it's better and it just means magic. Maximum likelihood is actually the origin of least squares. So it has least squares has its roots in the maximum likelihood method, and actually a lot of statistical things use maximum likelihood at their core. So it's kind of the way to do it from the most fundamental point of view. And I'm going to briefly explain that. I think, we'll do the likelihood explanation first, and I'll show you the demo. So this is just with a coin. So you toss a biased coin 6 times, and you're trying to figure out, is my coin fair or is it not? We can figure out the likelihood of the bias of the coin. So this is our model. So every time you toss the coin, it's either going to be heads or tails. We can put in, that's our data. So the number of heads is going to be, if omega is our probability of getting a head, then this is how many heads we've observed. That's our data. And the number of tails is obviously the inverse probability. That's our observed data. So we put in our data here. We say we've got 4 heads in the sequence, we've got 2 tails. Then we can basically fit for omega. So this is really kind of backwards to what you would normally do. Normally you would say, we've got our data and we want to, you've not got your data. You want to model, the forward probability. You say, I've got a coin and it has this bias. Then what is the result going to be? This is kind of undoing that. So this doesn't give you a probability distribution. It gives you a likelihood distribution. And this is it doesn't sum to 1, for example, is quite important. And the peak of this curve tells you the most likely result, so the most likely omega, and that's 0.66, as you could probably trivially have guessed. But you also get the shape of this whole curve. So just like a probability distribution has more information than just, say, the mean or the standard deviation, you have the other higher orders moments there. The whole likelihood distribution gives you information, and we can use this to figure out how certain we are in a particular result. So before I talk about MLE for peak overlaps, this is MATLAB. This is what you should have when you open MATLAB. If you have downloaded the Atom Probe Lab zip file from the website, you should, and then you've navigated it there in your folder window here. So you find whatever folder it's in and you go there. a key thing to do is to make sure you add the source folder here. So a lot of these demos, they do this for you, but I'm just going to explicitly state it here. Make sure you right click on this, add to path, selected folders or folders and subfolders. You can also accomplish that with the add path function, which I guess is something like that, // yeah. That will add the path. So then you've got it in your MATLAB now knows to look in this folder to find the functions that you're calling. I really hope that this doesn't conflict with the toolbox which you may have loaded earlier in the school today. We'll have to wait and see whether people have issues with that. So the Atom Probe School Demos live script is something that I wrote for this presentation. I've got, it should be standalone that you can read this. This is just describing what I just showed you with the dice experiment. So this is setting up your Matlab variables. I'm just going to run that. You can now see in our workspace we've got a whole bunch of things here. Kind of important, the abundance table. So just highlight and hit F9 to, maybe I should make this a bit bigger actually. Is that maybe hopefully slightly more visible? This kind of codifies the probability or the face distribution of our die. It should be straightforward. If this is our composition A and B, which is, I said 42. In this case, I've set it to be exactly 42 and 58%. Our multinomial probability, and this is going to be important for our model, is the matrix multiplication of these two things. So you've got a 2 by 4 table and a 1 by 2 table, and when you multiply those two together, you get a 1 by 4 table here. As our result, our multinomial probability. And this just describes the heights of those peaks that we would observe in a perfect experiment. But we've already lost the information about the composition of A and B. It's now kind of been encoded into this probability. So you're not really going to have to worry too much about that. It'll make more sense when I show you the other general maths. We can simulate a multinomial random probability by using this function, mnrand, multinomial random numbers. And this is just like a binomial, except instead of having two options, you can have as many options as you want, which is exactly the case we have. We have different peaks, and if you evaporate a certain number of ions, it has a probability to fall into one of those different bins or buckets or mass bins that we have in this case. So up here, we've got a number of die we're tipping out at a time, and we've got a number of times that we're going to repeat this experiment. And that's this particular result. The keen-eyed among you will have noticed that I fixed the seed. So whenever you run this, you should always get the same answer so that your script agrees with mine. Later on, I would recommend remove that, set it to the default, or just don't have it, and then you'll get different answers every time, and that's always more fun. So each one of these rows is an individual result of our experiment, how many counts we got in each mass peak. So 4 in mass 1, 2 in mass 2, 6 in mass 3, 2 in mass 4. Let's use the single peak method to figure out our composition. To get the total number, I'm going to take the first column and the second column of our result, and I'm going to add in the third column but take away the fourth column. So that's just using basically the fourth column, the fourth mass peak that's not a peak, is not in the peak overlap. We're just subtracting that from the third column to just leave the A, the number of A, atoms, and I'm dividing by n, which was the number of dice in total, to give a composition. And we get these, what look like spurious results here. So 30%, 0. 71%. This could even be negative. So this is, you can kind of see this isn't a really great approach. The other thing we can do is we can use least squares, and again, this minimizes the sum squared residual. I'm using specifically the LSQ non-neg function. Atom Probe Lab uses the optimization toolbox. I think this is a base function, but I'm not 100% sure. In the README, it does say what you need. Curve fitting and statistics. So, okay, so it's not optimization, it's statistics, I think. That might even be true of the multinomial random distribution. I apologize if you don't have these toolboxes. For a lot of the functions, it's very difficult to write another base function that does the same thing. So for the moment, I'm just going to apologize, and you'll have to either buy those or not use those functions. So this looks a little complicated, but it's just because I'm using a loop to store the results. This function doesn't take an array of our simulated results. It just takes an individual row at a time. So this is a very straightforward for loop, and I'm dividing the results by n because, again, this is giving us a number of counts. So to get composition, we divide by the total. And we can see we've got our estimates. These look a little bit more reasonable. We're using all the peak data here. Now we're using the maximum likelihood method. This uses a solver which is built into AtomProbe Lab. So this is where if you've not added your source folder, you'll get an error saying it can't find this function. You can see it works very similarly to the least squares solver, that you feed it an abundance table, you feed it a simulated result. It also needs an initial guess here. So 0.5 is my initial guess. In simple cases, it's not biased at all by your initial guess. When you have really complicated peak overlaps with sort of 10 or more ions all involved in your overlap group, then it might become sensitive to your initial guess. And I've been fairly careful how that's defined in the rest of the code to make sure that's consistent. You shouldn't really need to worry about this, but just to mention that it is there. You do have to specify a starting point. It is a numerical optimization. It's not an analytical result. These are our results for the maximum likelihood solver. You'll note here it's actually returning composition, not number of counts. So we can summarize this and look at the mean and standard deviation of our results. So the top row here is our single peak, the second one is least squares, and the third one is maximum likelihood. And this particular random seed shows the effect quite nicely, that the single peak is the least accurate and has the widest standard deviation. The least squares is better in both cases, but the maximum likelihood has the smallest standard deviation. Least squares may actually be it may be slightly less biased depending on exactly your situation, but they should, in terms of accuracy, the maximum likelihood should be better, and that's indicated by this smaller standard deviation. So that means if you could repeat your AtomProbe experiment, you're always going to be getting better, you get closer to the true value on average than you would do if you were using least squares. So I've just printed these out here as well in case you've changed the seed. So in your live script, you can go back up now and you can change the number of die that are being thrown and the number of tests. So I can have a go at that. If we increase the number of tests and I run this section, oh yeah, that's already updated. So this one's negative now apparently. We go back down to our summary. Now you can see that all of them get more accurate. If you've got more data, you're going to get more accurate results. But because we're basically just repeating the same experiment over and over and over again. That means we still have, because we've only basically got 14 atoms, we've still got really high counting error here, and that's indicated by the standard deviation. If we increase the number of die that we throw, then you'll see that the standard deviation also is reduced, and the maximum likelihood still the best option there. So and that comes down in a sort of root n manner, as in that equation that I showed you before for the counting error. So as you increase the number of counts, your counting error is going to get better with the square root of the number of counts. So if you increase it by 10, if you increase it by 100, it's going to get better by a factor of 10. So yeah, I will encourage you to go away, play with those. You can change the composition values if you want. you could do whatever you want with that and run it and see what happens. This is the maths behind that, and this is given in this paper down here. This is basically solving a matrix equation. The important thing about solving matrix equations is that it needs to be, constrained or over-constrained. If you have a rank deficient problem, that means you've got more ions than you have peaks. Then you're going to have it's basically numerically and mathematically undefined, and you can't give a distinct answer for what that should be. And very simply, it can be expressed in this kind of mathematical way. So it's based on the probability here. This is this is statistics language, the chance of all results from fixed parameters, and this is just our composition. So the probability translates into composition of different ions. The likelihood, this is how likely we are to get the right answer, which is slightly different from probability. And then we have some output number of counts that we get in our different peaks, and this is multiplied by the total. So because this is actually a multinomial formulation, it's always dependent on the total number of counts, and it kind of cancels out in the maths, but if you do the full thing, you've got a whole bunch of extra terms here. The likelihood is proportional to this value. It's not equal to it. I guess that's my mistake. So let's just switch back to Matlab, and I'll show you a little demo of this. In this case, I've got two ions, and this introduces the cell array format that AtomProbe Lab uses. So rather than using spaces, I have these cell arrays which define my ions. So there's a big cell array. The outer list here is just a list of different ions, and the first ion is the 2+ charge state, chromium, and the second one is the 2+ charge state ion. If we wanted oxygen in here, so iron oxide, we could add O. If you want two of those, we just add a 2. It assumes there's a 1 if you just add another element at the end of it. So it's reasonably natural, but it's verbose enough that later on you'll see I show you how you can just kind of write something. Instead of that, you can just write like Fe2O++, and then it will, using the rules that elements are only 2 or 3 characters long and a number of pluses, you can figure out what ion it is. This makes an abundance table. So this actually includes the peak position as well as the abundance of each of the different ions. So the columns here are the different ions. So this one's chromium and the second one is iron. Is that correct? That doesn't look correct. I think I've overwritten that later on. Sorry. And that's actually that way. Yeah, that looks more like it. So we've got the chromium abundance here, we've got the iron abundance here, and we can see at this peak in the middle they overlap. So peak heights actually has a tolerance for whether it considers peaks in the mass spectrum to overlap. And you can set that. There's other options to this in terms of the minimum abundance and the start and finish range widths that you want to use. You can look at the documentation if you're interested in that. Composition, let's just say 30-70%. I'm going to times by 100, so we've got 100 total counts. This is our log likelihood function as defined in the PowerPoint presentation. So again, this is just the magic of the maths here. And then we have a plot which shows the log likelihood as a function of the composition. So we're inputting composition and we're getting out log likelihood, and what we want is the most likely, so that's the maximum here. And as you can see, it matches up with 0.3, which is that's what we put in, that's what we get out. We can we can play with these values. We could change this to 10%, 90%, and that shifts the curve over. And the shape of this curve is important. So here I've basically just copied and pasted the same code, and here we have silicon and iron. Now these overlap kind of more strongly, and I'll come to that in a moment. And when we put those in to the let me change this back because it's actually using the same result later on. As we change the overlap problem, so this isn't changing the number of counts and it's not changing the underlying composition, it's just the identity of those ions which overlap. Now you see we get two different curves. Again, because of the other multinomial factors that don't vary as a function of composition, the absolute values don't quite make sense, but you can see that the shape of the silicon ion overlap is different to the chromium ion overlap. And that's because we're kind of injecting extra information about our problem by using the mathematical equation. So let's have a look at that. All right, we're back to our PowerPoint. So maximum likelihood gives us, the point at the top, that's the maximum, but it also gives us the full likelihood function for that particular data. So our model, informed by the data, gives us our likelihood distribution. And we can use this to get an idea of the uncertainty of our results. So this is a what's called a Wold test. You just go from the top, you go down, I think it's 2 log values, and then you draw across, and this gives you a 95% confidence interval. Very straightforward. Obviously, the shape of this curve is going to give you either a narrower or a wider distribution in your estimated composition. This is a little diagram showing some different ions overlapping with each other, and I've represented that as a overlap diagram. So this is a kind of a technique that I coined, and it shows in a simple snapshot which ions are present. So this is your mass spectrum. You can see we've got chromium, carbon monoxide, iron, nickel. We have those bubbles on the right hand side here. Which mass positions they overlap at. So this says that chromium and iron have the mass position 27 in common. And if we look over here at this diagram, you can see they do indeed have that mass position in common. And the same for the other peaks. The thickness and the colour, the intensity of the line, actually indicates how uncertain that particular overlap is. And these lines do kind of influence each other. So by adding carbon monoxide here, we've made the nickel iron and the iron chromium overlap wider as well. So it gives you, for a single overlap problem, for a single definition of ions, without knowing what the counts are, just assuming, say, all the counts are the same, it can tell you very easily whether you have an easy problem or a difficult problem. So the carbon monoxide overlaps, directly with the iron here, and so you could kind of guess that makes it more difficult to solve, as opposed to the 27 peak, the iron chromium overlap. There's very little overlapped intensity here, so there's much less information lost when those peaks overlap with each other, and the overlap diagram captures that. So let's have a quick look at how to make overlap diagrams. I put a table of contents at the beginning here, and they are the penultimate thing, so Control-click to follow links. Overlap groups. So I've copied this from one of the other scripts here, but it's in the live script for you to have a look at. You can give this kind of natural list here, so you're just writing this is carbon 2+, chromium 2+, iron 2+, carbon monoxide, nickel 2+. So you can write whatever you want in here. Those are the ions you're going to get in your overlap diagram. All of Atom Probe Lab doesn't know anything about isotopes. So if you want to do isotopic doping, you have to modify the isotopes table, which I guess is one of the sort of ground truths of the program. You can add whatever elements you want. So if you want to just sort of add uppercase O, lowercase o, something like O, whatever. If you want to define a new element which has a mass position 18 and 100% abundancy, then you can do that, and that's kind of defining a specific isotope. And then as long as your range files and everything else uses that element, you could write whatever you want there. You could have like X, Y, or whatever you want. You can define whatever elements you want. So it's all customizable. But it doesn't handle specific isotopes. So this generates a string, a cell array of different strings. We can convert those to the ions cell array format, which is displayed. You can see a little preview there. It's not very readable, unfortunately. So when you hover over it, it says it's a 1 by 3 cell, which is not, actually the most helpful thing. If I look at the first one of those, you can see it's 1 carbon 2, so it's 1 plus, then it's carbon, and there are 2 of those elements. That was just the format I settled on basically, like, I don't know, 7 years ago, and it stuck. I'm going to figure out the overlaps using this function here. So if you're doing anything where you're figuring out compositions and you've got peak overlaps, the thing that you want to use is the overlap problem builder and the overlap and the mass overlap solver functions. This builds a structure. So you can see on my workspace on the right, OP is a structure. If I just look at it in the command window, you can see it contains a bunch of things. So this is the definition of our problem. You can, if you want, go in and edit these things. I wouldn't really recommend it unless you know what you're doing, but there's a lot of very useful information in here. So for example, overlap table is the peak positions and the abundances of those different things. So if you wanted to edit the abundance of one particular species, you could go in and do that just in the overlap problem if you wanted to. And this kind of gets around a little bit of having functions that take millions of arguments, because everything is packaged into this structure. So maybe a class would be a better thing to use here, but for the moment it's just using structures, and that's fairly straightforward and lightweight. For the next part, you're going to need graphics. You don't have to have the actual full app as I have installed, which generates this figure here, which I guess you'll recognize. You can use this website here. So this DreamPuff engine is an online or graphics renderer. So you can take the output of the file which is written. So in this case, this function here is going to take the overlap ions and the overlap table and write an image for you. So where is that overlap demo text? Let's open that outside Matlab. We can just copy. If you don't have graphics, you can just copy and paste that in here. And ta-da! And from here, if you want, you can change the output if you want JSON for whatever reason, or you want a PNG rather than a vector graphic. Then you can do that. You can also change the engine. So if you don't want dots, you can use a different layout. I would say, from my experience, dot is the best one. There's different options you can use to edit this if you want, but that's graphics rather than AtomProbe Lab. AtomProbe Lab just gets you the text, which defines the different nodes and how they're joined together. Okay. And in this case, because I have graphics installed and I've fed in the appropriate executable location, then it's actually going to render a PNG for me, and it's going to show that in the window here. So that's what it looks like. It's a bit... oh, wrong way. There you go. It's a bit big. So that's how to make overlap diagrams with AtomProbe Lab. And these are really, I would say these are quite helpful if you've got supplemental data and you just want to show, easily where your peak overlaps are. This is a nice kind of easy visual, straightforward way. If you've got really complicated overlaps, then it shows you have really complicated overlaps in a fairly straightforward manner. Great. So just to kind of hammer home this uncertainty principle, again, I've got this chromium ion, carbon monoxide ion overlap, and these are the log likelihood profiles. These are the corresponding widths. In this case, there's the same number of counts. So what we're looking at here is counting error, but it's counting error once it propagates through the overlap solving. And it's actually described, mathematically by we get a distribution of compositions out rather than a fixed certain value. So AtomProbe Lab can actually quantify this uncertainty for you, and when you get error bars, the error bars take into account these effects. Yeah, there's your confidence interval. Yes. So real life is actually slightly more complicated. I showed you about solving peak overlaps using maximum likelihood and the uncertainty, but in real life we have multiple overlap groups that have to be combined together. So this is one data set, And these are the different separable mathematical problems that have to be solved, as well as the non-overlapped peaks as well. When we look at the composition, we don't want the composition of just one overlap group. We want the composition of the whole thing. We might want to do atomic to weight conversion. So, tungsten carbide, if you change that into weight percent, now the tungsten is much, appears much more prominent because it's heavier. You've also got other variants from different sources like background subtraction, or maybe you want to include the uncertainty from your abundance data. You might like to exclude particular elements. And I think you can do that all analytically. My solution in Atom Probe Lab is to just do a Monte Carlo simulation where you vary the input counts. And this can include whatever you want. So after you've got all your results, you can do your atomic to weight conversion. You can delete hydrogen. You can try multiple background subtractions and see how the results vary. So we just throw basically lots of random simulated data based on assuming that your original peak counts are Poisson distributed, which is, I think, a reasonable assumption. It means you don't get negative counts. It means you get kind of more or less normally distributed counts when they get higher up, and that's tending to our normal kind of understanding of how our data is distributed. We solve each of these individual sort of simulated data sets, and that gives us a composition. And in this case, for each of these things, we've got a distribution. Our result is also a distribution. And we can run this for as many samples as you want to get a more and more accurate estimate of your uncertainty. So I point out that the estimate from your data is based on the values that you have, and the uncertainty is based on the average of these samples, or the distribution of these samples. So the number of samples you do is only for quantifying the error bars. You'll get more accurate error bars if you throw more samples at it. It's not going to change your average value at all. That's calculated analytically. So just very briefly, a real-world example. I've shown this before, so I'll just go very quickly. But C2 and C4 overlapping. This is a very tricky overlap. It's a real problem that actually was published in 1992. This is the data that they had. I think this is my fit of it with the amount of C2 and C4. You've basically only got these two really tiny peaks that you're pivoting on to figure out this much bigger peak, how much C2 and C4 you've got. If we use the single peak approach and we apply counting error as our confidence interval, this is how the grey bar is what you would expect just from counting error. But the variation you're seeing here is because of the peak overlap, making that much more variable. And the error bars here are so tiny that you can't even see them. So in one particular experiment, you might have one of these dots, and then your error bar, your confidence interval, is really tiny. And these are marked red for the times when you don't get the true value in your confidence interval. And if you know statistics, you know that what you want to do is capture the true value in your confidence interval. That's the whole point, and that's your coverage. So the single peak method in this example has 20% coverage. So these tiny little error bars that are on here are actually 20% confidence intervals, not 95% confidence intervals as you expect. The same is true for least squares. With least squares, you can use the residuals to predict a confidence interval. What stands out here is that they're kind of all over the shop. Some of them are big, some of them are tiny. The coverage here is about 65%, and with maximum likelihood estimates using a world test, now we've got a 94% coverage for a 95% confidence interval, and I would say that is pretty good. I'd just like to point out these trials are independent. I've just sorted them by this maximum likelihood thing at the bottom, just kind of to guide the eye. I mean, it's actually just random. But the important thing is that we've got the smallest deviation. We're getting an accurate result. This was kind of, again, this was using a ground truth of exactly 60% to see what would happen. But we're getting the right sized error bars. So the important thing here is the error bars are bigger, but they're correct. And that's maybe not what we want to hear. We want really small error bars. But if you put really small error bars, you're misrepresenting your data. So there are some disadvantages to using maximum likelihood. It's more difficult to understand, so when you're explaining it to someone, you can't just say least squares and assume that they know what they're talking about. We're moving beyond IVAS and Excel. I guess I'm talking to the converted because we're all using Matlab now in this particular school, but it's a more difficult to use tool than just clicking a button in Excel or IVAS. There are some numerical stability issues, especially when you get to using very many ions in a particular overlap. If you get to more than 15, that's basically a 15-dimension problem, and that's hard to numerically estimate. And it's slower than least squares, but it's not really hugely slower. It's only slow. You only really notice that it's slower if you have to do tens of millions of calculations. There is a kind of important bias that comes in at low counts, and this is not just for maximum likelihood. This is true for everything. But I think before we do that, let's do something a little bit more fun and look at some plotting. Have I totally lost everybody, or are you still with me?
I'm trying my best.
That's great. It should get a bit easier from here on. So let's look at the mass spectrum simulator and the plotter. AtomProbe Lab includes a mass spectrum simulator tool for you to use. The input, it's all written out here for you to look at. It uses this table, and I'm not. When I came up with this, I guess I wasn't. No, wants to say I wasn't thinking clearly, but it's not the kind of easiest to understand format. The idea is you have an element or a molecule, you have an amount which could be balance, which was a nice little trick to just say everything else. This is the composition in percent, so 10% chromium, 5% aluminium, 9% nickel, and it's 4% iron hydroxide or something. You've got some particular width of your peak, which I guess for the most part we'll just ignore, and then we've got a distribution of different charge states. So I think this makes sense if you have your data formatted in a particular way. I think if you've actually got a composition and you want to then simulate it, this isn't the best tool. This isn't the easiest way of doing the input. I think there is actually a function which will do that conversion for you. So you feed it an ionic composition and it will spit out this ion input table for you. But let's assume you've got this ion input table. We're going to use the mass spectrum simulator. We feed it a total number of counts. We feed it a noise count as well. Optionally, you could just set that to 0 if you don't want any noise. And we feed it this table, which defines the composition of our different peaks. It's going to use the isotopes mat file, which is in the source here somewhere, to define the abundance of your elements. And this empty thing here is the peak shape. I guess this actually should be peak shape. I apologize. I'll have to change that. So that's either blank if you want a real shape, which is the default. You can have norm for a Gaussian shape or normal shape, or you can have delta if you just want individual sort of spikes, which is really helpful. Here we've got the resulting elemental table, the elemental composition and count table. So this spits out a Matlab table that tells you how much of each of these elements you have, and this is doing the decomposition from this complex molecule into an elemental, a number of elemental counts. It's also got the composition as well. So if you then take this mass spectrum, so this list of masses that you've got, and then you figure out what the composition is, you want to compare it to, say, this elemental composition here. And because what we're doing is subject to random chance to some small amount, then you need to know what the actual composition was, not just the one that you specified. Because if you've got very low counts, it might be different. If you have one more atom of something, that could change the composition if you've only got 10 atoms in total. Let's plot what that looks like. And I'm being a bit lazy here. I'm using the overlap problem builder again and a list of ions. So I'm using the ions. The ions come from this ions names thing. So this is actually the output of this particular function. It spits out the ions that it's generated. Because these are all ones and zeros, I've just got aluminium 1 plus, Fe 2 plus, etc. You can have whatever charge state you want here. Just add more columns for more charge states. Yeah, I'm using the overlap problem builder to generate a range file, which is, I think, really backwards. But when the only tool you have is an overlap problem solving tool, then everything looks like an overlap problem. I use the overlap problem to ranges function to turn my structure into a range cell array, which actually contains all of the information about the range file. So the elements, the ions, the mass positions, the colors, the volume, that's all stored in this little cell array here. And then we're using the mass spectrum plotter. So this is where we get to the mass spectrum plotter, which I'm reasonably proud of. It's the work of several years worth of work to try and optimize the what this looks like. And for some reason, it's very tall. Maybe because I exported it as a PDF. If anyone knows how you change the default sizes of these things, I'd be appreciate it, because it didn't look like this before. It's a bit taller than I had before. Anyway, yeah, this is the mass spectrum plotter. So we get the colored ranges in the mass spectrum as you'd expect, and then it's got these labels above it. So these, I tried putting the labels on the individual peaks. I found that annoying, and then I was frustrated that I didn't have the natural abundance information. So I came up with this. I looked at a whole bunch of different mass spectra in the literature. So not in Atom Probe, but in other fields. And in biology, they often have very complex molecules, and you don't want you want just to represent where they are roughly. You don't necessarily need to label each individual peak. And then I came up with this kind of like bar or like sort of spectral format to show where the peaks are, and the width of these bars actually indicates their abundance. There's a stick option I'll show you later on, because that's a little bit more, especially in linear space, it's easier to interpret. But the bright, the wider the bar here, the more intense that peak. So this kind of gives you a sense of where you've got different peaks and where they overlap. So here we can see we've got chromium, aluminium, and iron. They all overlap here. I think in my examples, I often use these ions. Atom Probe Lab does work with any ion. It's not just iron, chromium, and aluminium. Those are just my sort of like go-to thing to look at. We can try changing the peak shape. Let's change the peak shape to norm, I guess, and see what that looks like. So it shouldn't change the counts of anything, but when we run the mass spectrum, now we've got Gaussians instead. We can change the width here. So let's just like bump up the width to 100, and this is just like a linear scaling in time of flight space. So now we've got enormous peaks that look terrible. But yeah, that gives you the ability to simulate a mass spectrum and to plot the results, to take that mass list, and you could save it as a POS file with some like random XYZ data, load it into whatever else you want to do, and see how that compares. So it's very useful having simulated data where you know the actual answer, and then you can compare that to other compare that to the real value. So it's I would say it's really useful having that kind of tool. I found it very helpful looking for errors and things like that. I'll just briefly show you some of the options for the mass spectrum plotter. I guess take a look in the live script at your leisure. This is the default output, which looks, I guess let's go back to the correct, or not the correct, but the sort of semi-realistic looking mass peaks. Just so I think it looks right. So this is what it looks like. You get 3 panels, which is useful if you've got lots of data. Not so useful in this case because we've only got a small sort of region of data, which means we can use the minimum and maximum options. So just like the Matlab plot function, you feed this name value pairs. So in this case, min m and then 24 for the minimum mass, and max m 31.5 for the maximum mass. And now you see we're just plotting, just that narrow range. And the num here means num is short for number of panels. So that's how many plots, subplots we're making. So we can easily control that number there. We can change the font size to make this more clear, which I think immediately looks a lot better. We can switch between the log value and linear space. We can control the number of histogram bins, so histogram bins. For any of these values, these names here, you can you don't have to write the whole thing. So the actual option is histogram bins, but you can just write hist or even just h and that's still unique. So as long as the match here is unique. So M is not unique because it could be minimum or maximum. So some of these options you can shorten more than others, which is useful. You can use the bar, the abundance style as bars, like in this top example, or you can use the sticks. So these are the kind of more classical sticks, and these are normalized to the maximum abundance. So nickel, for example, you can see that the bar goes all the way up to the top, and that's, especially if you're looking at things in linear space, I think that's quite helpful. If your scale here is in log, then these are displayed, the abundances are displayed in log, and if they are linear, then they're displayed in linear. That makes sense. We can also, to save space, you can stick a bunch of options in a cell array and then just use these curly braces with a colon in the middle, and that's like MATLAB shorthand for just give me all the contents of that cell array. So you can see down here, it just gives me all these different answers for all of these different things. So for any arguments, you can always stick a bunch of stuff in a cell array. If you want to call this multiple times, it's really quite useful to just stick, I always want these options. So just stick those in there, and then you can feed that in at the end. And then the last example here, there's a whole bunch of code, but that's because the more you want to, with any kind of programming, like programmatic plotting, the more customization you want. Everything you want to change is like another line of code. So if you want to change the X and Y labels, that's each a separate line of code. There's some tweaking here to change the position, which you can play about with, but this saves a PNG. You could save a vector graphic if you wanted, but this saves a sort of high resolution bitmap, which is very useful if you're presenting in PowerPoint or something, to have it as a bitmap. But that's how you can get reasonably nice looking figures out of MATLAB, and that's sort of written down for you to tweak and play with and do whatever, so that you can use that whenever you want or however you want. So that's the plotting. I hope you're a fan of the different label options. Like I said, I think this is a fairly clear way of showing what's involved. Again, it doesn't know anything about isotopes, and that was, I think, partly motivated by, so if you've got like Molly 3, then in each individual peak you've got 3 or 4, however many it is, different possible isotopes that you're combining there, and so it gets really messy. But I mean, I'd like to talk to Peter and others and get their ideas. I'd also, if you've got applications where isotopes is a real motivation, I'd love to hear about that, because having a need is what drives the innovation and the change. So let's pop back. Let's talk about bias for a moment. This is not unique to. Oh, people are chatting. That's good. This is not specific to any. This affects everything. So. You have this kind of what I call the monoisotopic limit, which means if you have a few counts of something, a species can appear to be monoisotopic. That means only having one peak. And for example, different elements here, titanium, carbon, oxygen, and hydrogen, these are how many counts you need to avoid a 1% chance of only getting the main peak. So in carbon it would only be the 12 peak, in titanium it would only be the 48 peak, in oxygen it would only be the oxygen 16, and for hydrogen it would be only the protium. So if you've got titanium, you need really more than 14 counts of titanium to be able to get any kind of a hint that it's something other than just a peak at, say, 48. So if you had carbon 4 and titanium, you can't tell those two apart at all if you've got less than 14 counts. And the same for hydrogen and deuterium. So, your hydrogen is going to appear just in the one peak, 1 in 30 odd thousand, 30 odd thousand times out of 30 odd thousand, and it's not going to show up any natural deuterium in the 2 peak. So this is a problem, say, if you've got Ti3 plus and O at 16 Daltons, you would mistake your titanium as being O if it's got really small counts. And there's basically no way around this apart from having a better detector, like a kinetic sensitive detector. That doesn't help you if you have the same charge state ions that overlap like this, though. So just to be aware, this is the equation you can use given the big P being the level that you of confidence you want. So like a 1% confidence, you want to avoid it 99% of the time. And little p is the abundance of the species you're interested in. So from titanium, it's like 75%. Carbon, it's like 99%. So, in your data, you can figure out what this limit is and then make sure that if you're doing anything where you've got small counts, so proxygrams near the center, cluster searches, single ion overlap solving, anything where you've got voxels, which are quite small, you need to make sure you've got enough counts that you're avoiding this bias. So that's just one particular bias I just thought I'd highlight there. Something else that's really important, I was glad to hear Peter mention, make sure that you've got the sticks in your plot so you can see whether your ranged ions match up with what you expect. Goodness of fit is a sort of formal way of measuring that, of quantifying that. For example, chi-squared, the fit for this particular choice, the chi-squared p value is 0, where the p value is like the p value we're familiar with. Anything less than 5% you would maybe consider as being significant. The p-value here is 0.0027. So this is still really tiny, but you can see the fit here is really good. And this is kind of a consequence of having so many counts. The more counts you have, the more sort of sensitive your p-value becomes. So chi-squared is maybe not the best solution. My ion fit tester, which I'll show you in a moment, uses the effect size, which I think is slightly better. But yeah, this is basically just a way of showing whether you've got the right ions in your fit, whether your fitting procedure is converged or not, whether you have isotopic specific hit loss, or whether if you've got wrong background subtraction. Goodness of fit is really important, and actually I think we should be reporting some measure of goodness of fit whenever we do any kind of composition, and it should always be there so other people can inspect it and check that what we've done is correct. So whatever kind of composition measurement you're doing, always check that your peaks match what you think you have, because if they don't match, you don't have what you think you have, and then your composition's wrong. Very quickly, I don't really want to talk about information theory. Again, it's a sort of a magic number. This is the Akaki information criterion. It's based on the information loss as estimated from this Kullback-Leiber divergence. It's a way to find the model which is most likely to have lost the least information. So it's the way of finding, quote unquote, the best model from the models that you provide it. And it's really useful because it just depends on the number of ions. So parameters is our fitting parameters, is the number of ions, and the log likelihood. And hey, we've just got a thing where we've been talking about maximum likelihood and we've got the log likelihood value. So the lowest AIC value here is best. So by adding more parameters, that's making, that's kind of penalizing us from just adding more and more ions, right? You look at a mass spectrum and you start adding increasingly like random ions in order to, it's like, oh, I'm getting fewer and fewer, getting better and better residual. I've got fewer unranged counts, so it must be getting better. But actually, you're kind of overfitting your problem, and maybe you're introducing ions that it's not statistically justified in adding them. And this is a way of avoiding that problem. So this function penalizes overfitting, and the likelihood value rewards better fit. So it's a very simple expression. So this is, again, a real example from literature. I think in zirconium, where there's a potential for carbon monoxide to be included in this set of peaks. And you can see the green here is carbon monoxide, and it hides in this 28 peak. So if you include it, there's only a tiny amount of it in there. But maybe that's important because carbon monoxide is a contaminant and iron is the actual thing you're interested in. So, maybe you need to consider it. In the paper, they concluded that the relative isotopic abundances agree within the margin of error, and they didn't include carbon monoxide. So was this a good choice or not? Well, we can look at the residuals, the sum squared residuals, and in this case we're fitting exactly to the data, so there's no residual. So you're like, great, excellent fit. In this case there is a residual. The AIC value, we said the lowest AIC value is better, so this one is better, but it's only better by 1 unit. And actually in statistics they say you really kind of need at least 2 for it to be considered truly better. So it's what this actually tells us is it tells us the choice is marginal, so there's not really strong evidence for using one or the other, and it's quantifying how marginal that choice is. So we're going beyond should we include it or not. We're actually saying what's the evidence, what's the weight of evidence behind that, statistically speaking, and whether we should include that ion. And there's a fun function in Matlab that does this for you. So this is the ion fit tester. Let's have a look in the live script. Again, I'm going to go here. Where is it? Ion fit tester. It's right at the bottom. Okay. Control click to follow the link. So this is taken almost entirely from the demo script. So AtomProbe Lab has a bunch of demo scripts that you can use. There are some parameters here that you probably don't need to worry about. I'm loading here. You would load a data set. Here I'm simulating a data set using the ion input mass spec simulator as shown before. This is what my mass spectrum looks like. So it jumps out as being synthetic, but it's it's got a bunch of different peaks. Some of them are overlapped, some of them aren't overlapped. We've got our old friends, old friends, iron and aluminium and things in there. Reading this is kind of cheating because this is the answer. Okay, so you would be presented with this mass spectrum in your experiment. You wouldn't know what the true composition is. So here, for example, I'm including carbon monoxide, but there's no aluminium here. Okay, so we're not including aluminium, but we do have nickel and we do have iron. So then what you would provide is your list of potential ions, and this includes silicon. So maybe you look at your mass spectrum and you say, hey, that ion peak looks a bit tall. Maybe it's got silicon in it. Maybe it's got carbon monoxide in it. What's a good choice? Should we include silicon or not? If we include silicon, we're going to see silicon in our result. If we don't include silicon, there's going to be no silicon. When we run the actual function, which is the ion fit tester down here, so shall I zoom in again for people so you can see? When we run the ion fit tester down here, it's going to take every combination of all of those different ions and try and estimate the composition, figure out the information loss, get the goodness of fit, and that's a lot of calculations if you've got lots of ions. So you can sort of help by adding some mandatory ions. So those are always going to be included. So if you've got, it's a steel, it's always going to have iron in it, or it's a titanium alloy, it's always going to have titanium. You speed the calculation up by adding those mandatory ions. This is the actual function, which I guess has quite a lot of outputs. Very quickly going through them, it talks about the non-overlapped peaks, which just fits the non-overlapped peaks. The report cell is the thing which for each overlap group, so it separates it by overlap group to simplify the calculation, you get this sort of big, scary dump of information. Just reading across from left to right, you've got the AIC value, the actual raw value. We've got this sort of normalized probability, so relative to the best ranked model, these are ranked in order of sort of lower AIC value. We've got the effect size, so you can see things that fit badly. So you can see down here we've got like 0.17, 0.2 or whatever. This represents bad fit. So the higher effect size is worse, smaller is better. In this case. And then at the right hand side here we've got the different species, and these are ranked by the composition that was measured. So the top one goes iron, nickel, carbon monoxide, and then flat is this kind of, it's this cheat that I have to add in to be able to compare everything. If you've got something that includes a flat, that just means like a flat background intensity. So in most cases you just ignore, if it says flat, you just ignore that. So our first two models, they have a value of about 73 AIC. The next best one is 75-ish. So you can say, okay, so this is probably our best solution. The next one here includes silicon, for example. Now our actual ground truth didn't include silicon. And what this is showing us is that we shouldn't include silicon. So this has made that statistical choice for us, and it's formalized it, and it's quantified with the effect size and all that kind of good stuff. If you go down, you can see aluminium creeps in here. If you go to these really badly fitting ones, you dump iron altogether, and it just tries fitting silicon or carbon monoxide. It's kind of, the computer's getting increasingly desperate, and you can see the AIC values are totally ridiculous because they just don't fit at all. And there's another one down here for the iron hydride overlap as well. So for each overlap group, you'll get one of these plots. And this helps you to hopefully remove bias in the ions that you're inputting into your overlap solving. I've got a fairly complicated looking for loop here, which then plots each of those results. So this is the best one. This was the one with the flat intensity. This is the one without the flat intensity. You can see that the flat is light blue. I can't even see it, so it's obviously not that important. This is the one that includes silicon. Again, you can barely see the silicon, so it's obviously predicting very low composition of that. And this one's with aluminium instead. And again, the important thing is here, all of these fits look the same. So, if you actually did this, you'd be like, okay, I'm fairly confident now that I know what species are there, what's important, what's not important. I think this is giving Atom Probe users an insight that was previously missing when it came to choosing which ions they wanted to fit and how important different things were. So, hopefully this is a function that you'll be able to use and find useful. I'd love it if this was integrated into, say, the Atom Probe toolbox, and I'd be happy to help. Do that. So very quickly, just on the AIC, it has a kind of difficulty or sensitivity, and this is related to the overlap problem. So I'm banging on again over overlap problems. Silicon is harder to solve than, say, aluminium. So this is the plot. The abundance if we have silicon, and this is it with aluminium. Now, aluminium is in the 27 peak, it's started in the 28 peak, and that means if we were to simulate some data and systematically vary the amount of silicon or aluminium that was actually in there, and then try and fit it with and without that species, you can see if it's silicon, we need over 1.5% silicon in this particular example to switch from being with silicon to without silicon. So initially, your choice is, this is the normalized thing, so the higher here is better, so this is like 100%. So this is best, and then once you get past 1.5, then the without silicon drops down and the with silicon is correct. So below this concentration, even using this method, you would say we're not going to add silicon because it's not justified, even though it's actually there. So this is kind of like a false negative, I guess, that you're kind of you're removing it when you shouldn't do. And the aluminium, which is an easier overlap, the threshold is crossed a lot sooner. You need, only like less than 0.5% aluminium to be able to quote unquote see it in your data set and be statistically justified in adding it. So the AIC is not a panacea. It does not instantly make all of our problems go away, but it does quantify kind of how difficult these things are, and it helps us make statistically informed choices, not just like adding random ions, which I think is a little bit unscientific potentially. Okay, so when peaks overlap, we lose information. Maximum likelihood is great for solving peak overlaps. Atom Probe Lab can do that for you. I guess I haven't actually shown you any peak overlap solving, so I hope I've got time to just briefly show you an example of that, because it seems kind of remiss to actually skip that entirely. Different overlap groups have differing degrees of difficulty or intensity, and that means more uncertainty when we try and solve them. And there's nothing we can get. There's nothing I can do. There's nothing like maths can do to help you there. That's just life. AIC can be used to help make a good selection of ions, and always check your goodness of fit. Ask why your peaks don't fit and report it. And we should be holding each other to account in our published works. If we're not talking about the goodness of fit in our supplemental data or in our papers, then we're not doing good science. Strong statement, but there we go. I hope I'm going to stand by it, and I'll try and live by it. So thank you very much for listening. I will just quickly show you an overlap solved line profile using the demo script line decomp. So you should be able to download Atom Probe Lab, go to this script, hit go, and it should give you a line profile. So fingers crossed this works. So F5 is the shortcut to make something run. What this is doing is it's splitting the data set up into a number of sub-volumes which are along a particular profile direction. In this case, this is a vector, so it's across the diagonal of this data set. So it's 2 clusters. Spoiler alert, these are TiO and O2 containing clusters, so titanium oxide and O2 ions. Those things peak overlap, obviously, at 32 Daltons. And the line profile is diagonally across this, so it should separate out the 2 different, go from one corner to the next, and we should see one of them containing titanium and one of them containing oxygen. Weird. Okay, there it is. So I guess the colors are not so pretty. Thanks, Matlab default colors. But you can see across this data set, we've got the region in the middle here. There's not really; it's just noise. But in this region, it's very low titanium and very high oxygen, which is one of the clusters, which was mostly containing O2. And in the second one, it's pure TiO. So when we split that into an elemental composition, it looks like equal Ti and O. And this has got error bars. You can see the error bars are unequal because we're using the full power of maximum likelihood estimation, and that gives you unequal error bars. And that is correct. The error bars shouldn't ever go above or below 0 because that's also not correct for composition. And you can see in the region where we hit the clusters, which I think is this point here and this point here, the error bars are narrow because in the cluster there's a lot of counts for those species. Outside of the clusters there's very few counts, and that's why these error bars are much larger. But yes, you can use Atom Probe Lab to make peak overlap solved line compositions, line profile compositions, and hopefully that's useful for people. You can obviously also use it for bulk compositions. That's that sort of simple composition. You can use the bulk decomp script for that. There's a local one which does sort of single ion overlap solving, and I think the decomp parts one actually uses it's kind of cheating. You can actually use a cluster.index.pos file, so where each of your ions is labeled by which cluster it belongs to make a sub index list. And when you run this, it will this is like a cluster search where you've got the composition of the 2 separate clusters are separated out from that data set. And it says do something with the output. Okay, composition LE. So let's look at one of these. So that's the composition of the first cluster, and I guess unhelpfully it's not labeled, but this is the amount of titanium, this is the amount of oxygen. You'll have to take my word for it. This is the lower confidence interval, the upper one, and the average composition, and you can see that matches up quite nicely with our line profile that we did. If we look at the second cluster, then here we've got much higher composition. It's confusing to me, but I guess maybe no, it's not ionic, it is elemental. Oh, there we go. I guess this is either my line profile's not great or this is doing something slightly different. But there we go. That's what you get for doing things live. It can backfire slightly. I sort of thought this would come out 50-50, but it didn't. Maybe it's looking at the noise or something. But the names of those different things are titanium and oxygen. So this is the amount of titanium. This is the amount of oxygen. Yeah. Anyway, I guess that's it. I'm very happy to take questions, have discussions, whatever, if my camera's still working. Yep. Peter says never abbreviate anything if you can avoid it. Yes, but I'm also a lazy programmer.
Yeah, the The thing is, at one point, you will have to go back into code that you've written years ago, and you have to be able to read it.
Yeah.
That is,
it's an
it
excellent.
turns out the more verbose you can be, the better.
Yeah, I would never recommend anyone just putting in H when they actually mean histogram bins. Like, that's going to be really confusing when you come back to it.
Yeah.
Yeah.
And it actually would be really interesting to integrate, but because I think we've provided quite a fair bit of the infrastructure that's really going to make the shine, especially in terms of pre-guesses. So you could, for example, define a lot of ions and then go like, okay, these are all my potential candidates. Please give me a good estimate of what actually would make sense. And probably you'd have to make your physically educated choice of which one you would actually select out of those choices.
Yeah.
And of course, with the concentration determination that follows on with those estimates, that would also be something that would be really, really interesting to integrate. And maybe you'll see when we show how we do 2D concentration, 1D, 2D concentration profiles and the like, that once you have that kind of a little program, you can plug it into all of those different methods, and that would really, really be helpful for a lot of things.
Yeah, that'd be great. Yeah. Yeah, totally up for that. To answer my question I asked you earlier about development strategy, my development strategy with Atom Probe Lab is it's me, and I do it in my spare time for free. So I do it to benefit mostly myself and somewhat the community, but my time is pretty limited, what with having a young family and everything. So I don't have the development power behind it in the same way that you guys do. So I'd be pretty happy to have someone else more or less take this on and then use it, and I'll just fix bugs behind the scenes as and when they come up.
Yeah. So, I mean, obviously, I do not have a grant that pays for it either, but I will always donate some of the time that I get out of other grants to sort of keep that going, because it really sometimes makes things possible that aren't really possible any other way.
Yeah.
And that's kind of the purpose, right? We want to provide you with an infrastructure that people can develop their analysis based on.
Exactly. I'm going to stop recording there.